So let's take a look at this example here. In this problem here, we have the figure off to the left. You can see somebody pulling back, a plunger here, some distance s. We have a spring here. The K given to us is 500 newtons per meter. You can see our angle here is measured off of our vertical, with the center point being at the center of this curve here, and we have the radius shown here of 1.5 meters, and an angle given to us is theta. So in the problem statement, we know that it's a 0.5 kilogram ball of negligible size, which treating as a point, and it's going to be fired up a vertical track of radius 1.5 meters, so there's our radius right there, using a spring plunger with, again, a K value of 500 newtons per meter. The plunger keeps the spring compressed at 0.08 meters when S is equal to 0, so that's our initial condition there. Now they're asking us to find the distance S. The plunger must be pulled back and released so that the ball will begin to leave the track when our theta is 135 degrees. So they give us a lot of information within this problem statement, a lot of different values. So our plan of attack will be, one, we're going to draw out a free body diagram of the ball when our theta is equal to 135 degrees. Two, we're going to apply the equation of motion in the n direction to determine the speed of the ball when it leaves the track. So we'll be using an NT coordinate system. And third, we're going to apply the principle of work and energy in order to determine our S, which is what they ask us to solve for in the problem. So the first step in our solution is to create our setup page. So in this one here, we redraw our simplified diagram. There's our spring here. The spring constant K is equal to 500 newtons per meter. So you pull back a distance here of S. There's our theta angle there and our radius of 1.5 meters. So again, we know our mass right here is equal to 0.5 kilograms. Our R is 1.5 meters. Our K value is equal to 500 newtons per meter. And our theta is at 135 degrees. We want to find over here, the thing that we're looking for is the distance S. So that's what we're looking for. So we're trying to solve for. So again, we recall back to our first slide there, we had our plan of attack. The first thing in our plan was to come up with our free body diagram. So that's what we do right here. We have a free body diagram. So we can see, okay, we'll do this for our ball right here. So at 135 degrees. So we can do our angles right here. We want to do this in the NT coordinate system, so we put our ball up at 135 degrees, or in this case here, 135 degrees would be at 45 degrees off of our horizontal if we do out some trig there, because we got 90 plus 1 plus 45 is equal to 135. So we're off here 135 degrees. If we look at this angle right there, that's your 135 off of our vertical over there, which is 45 degrees off of our horizontal there. There's our normal force right there and our tangential force right there. In our normal direction, we have our N right here, and we have our weight going down. Our weight's going to have an N and a T component for it. So note off to the side here, so we're doing our free body diagram, weight acts downward through the center of the ball. Normal force exerted by the track, this right here, our normal force exerted by the track, is perpendicular to the surface, and the friction force between the ball and the track has no component in the NT direction. So that's our first part of our solution there. We have our free body diagram drawn out, and we have our notes off to the side how it relates back to our problem. For the next part of our solution, we want to look for the equation of motion in the n direction. So again, we're dealing with our NT coordinate system. We're going to deal with each of those separately as we look for our equations of motion, doing our summation of forces. So in the NT direction, we're going to first look at our n direction. And since the ball leaves the track when our theta, given to the problem statement, is 135 degrees, we know at that point there, our n is equal to 0, because there's no normal force from the track working back at it when it leaves the track at 135 degrees. So now we can simplify this down to summation of forces in our n direction. So we can do a little trig out here. We can say, okay, we have this reaction force here, so we have our n times the cosine 45, and t is equal to sine of 45 right there if we want to do our trig to break things down. So summation of forces in our n direction is equal to mass times acceleration in the normal direction, where we have our weight force right here. So W times the cosine of 45 degrees. So again, dealing with that direction, it's the cosine of 45 degrees to break that down for our weight force, is equal to mass times acceleration normal direction. Acceleration normal, we can recall the relationship for that is v squared over rho. So plug in our values here. Weight is equal to mg, mass times acceleration due to gravity, where mass is given to us as 0.5 kilograms times 9.8 meters per second squared for the acceleration due to gravity, times the cosine of 45 to get it into our n coordinate system. This is equal to the right-hand side, our mass, m is 0.5, and now we have our v squared over rho, where rho is our radius of our track there of 1.5 meters. So our only unknown in this equation is our v. So we can rearrange, solve for v, and when we do that, v is equal to 3.2257 meters per second. So now for the third part of our solution, we recall back to our first page. For our problem statement, we're going to apply the principle of work and energy. We're going to apply this between position 1, which is when our theta is equal to 0 degrees on our diagram, and position 2, where theta is equal to 135 degrees. So one thing to note about this is that the normal force N does no work because it's always going to be perpendicular to the displacement direction. So let's go to our general equation for our principle of work and energy. So we have T1 plus the summation of U from 1 to 2 is equal to T2. So kinetic energy plus the work from 1 to 2, summation of the work from position 1 to position 2 is equal to kinetic energy 2. So general equation for kinetic energy, 1/2 mv squared, but for position 1, so it's 1/2 m1 v1 squared, minus the work here. Well, what things are, where is the work equations coming from? Well, we have one from our weight, which is the weight times the change in our y distance here, w times delta y. And we have now our spring force here, 1/2 k s2 squared minus 1/2 k s1 squared there. So that is this portion of our principle of work and energy problem there, is equal to the right-hand side, our T2, our kinetic energy 2, 1/2 m2 v2 squared. So now that we have this general equation and we plugged everything in, expanded it out, let's take a look at each individual variable along the way and figure out what we know. So we know that m1 is equal to m2 is equal to m. Mass doesn't change the ball throughout the entire problem, so our m1s and our m2s are both going to be the same. We're going to call that m. Our v1, our initial velocity, starts at rest. So v1 is equal to 0, so we know that goes to 0 there. Our v2 we solved for in the first part of the problem. We found that to be 3.2257 meters per second squared, so we have a value for v2. Now s1 is equal to s plus this length that they give us right there in the problem statement, or 0.08 meters. Our s2 is that 0.08 meters. So we've got to add that in when we're solving for our s1 there. It's s that we solve for plus our 0.08. Now our delta y here we can take from our diagram down here. We can see where we call our 0 point. We have 1.5 plus 1.5 times the sine of 45 degrees. Now why is that? Well, our distance from where the ball starts right here up to the center is that radius. So that's 1.5 degrees. Now if we're going all the way to the top, if our theta was 180, it would be 3. It could be 1.5 plus 1.5. But it's not. It's right here when theta is 45 off the horizontal or 135 off of our vertical. So that distance here, y, that we're going to add to this 1.5 is given by this triangle right here. So 1.5 times the sine of 45 will give us that right there. So that's where we get this distance here, 1.5 plus 1.5 times the sine of 45 will give us a value now for our delta y of 2.5607. So that's the distance from y down to our origin here. So this right there to that right there, that's our delta y. So now we can take all of this information that we have here and from our diagram here that we plug back in for delta y and plug back in to our expanded form of our principle of work and energy. So we do that there, we plug in, we end up with 1/2 of mv, where v is 0, so this whole term is going to go to 0 because we have v1, our initial velocity, at 0 from our initial conditions, minus our work, which is mass times acceleration due to gravity, times our delta y. We just solved for our delta y. We know our mass is 0.5 kilograms. Acceleration due to gravity is 9.81 meters per second squared. So we can plug in numeric values for all that there. Then we go up to 1/2 k s2 squared, where our k is given to us as 500. There's our 1/2 right there. There's our s2 right there from the problem statement, 0.08 meters, minus 1/2 k s1 squared, where s1 is s plus this 0.08 right there. So we can plug that value in there. So now we have everything in terms of s. So our s1 and our s2 go away now within this equation here. And this is equal to 1/2 mv2 squared, which is 1/2 our mass of 0.5, and our V2, which you got cut off with our hole punch there, is our 3.2257, 3.2257, and that is in meters per second. So we can plug and chug this whole equation here, solve for our S, and what we find is our S is equal to 0.179 meters.